Hello guys, we'll start our practice lesson, Higher Mathematics 2, Practice 4. Practice on the chain rule. In the lecture part of the chain rule, we saw some theorems and definitions, how to calculate the derivatives of single variable and double variable functions with some intermediate and independent variables. Now, let's try to check some examples and try to solve some good exercises on the theme. We saw this example in the lecture part. You may refer to the lecture video and the lecture PDF. We'll first recap this one. So w equals to xy. This is a given function, double variable function, double intermediate variables. X and y are intermediate, and this one x equals to cosine t and y equals to sine t. Here is that t is independent variable. So how to calculate the derivative? There are two ways to calculate this. The first one is just to calculate this derivative using chain rule, and the second one is calculate the derivative by replacing x and y with the independent variable, which is cosine t and sine t. But we are learning the chain rule, so it's better to use this one, dv dt. We have to calculate this one, dt equals to partial derivative of w with respect to x times dx dt plus dv dy dt. If you remember, I'm writing this kind of d to know that this is the partial derivative, not ordinary derivative. So partial derivative of w with respect to x gives me y. Partial derivative of x with respect to t gives me negative sine of t, plus derivative of w with respect to y gives me x. Derivative of sine with respect to t gives me cosine t equals to y is sine t, so I write sine t here again, times negative sine t plus x is cosine t times cosine of t equals to negative sine squared t plus cosine squared t. This gives us cosine of 2t. So this is the answer, and we have to plug in this number here, which is t equals to how much? Pi over 2. Okay, let's plug in pi over 2 instead of t. It gives us cosine 2 times pi over 2 gives us cosine of pi, which is negative 1. So here is how to calculate the value of the derivative at point t equals to pi over 2. We also got this negative 1. Okay, go further. This is second example. We also saw this example in the lecture part, which is w equals to xy plus z. X equals to cosine of t, y equals to sine of t, and z equals to t. So in order to calculate, we use this chain rule formula. Derivative of w with respect to x gives me w with respect to x gives me y. Derivative of w with respect to y gives me x. Derivative of w with respect to z gives me 1. And I've just calculated all of them, the first terms, and the next one, dx dt, dy dt, dz dt can be calculated using these formulas, because we already have x equals to cosine of t, y equals to sine of t, and of course z equals to t. We'll calculate that at last to us to calculate the exact value of that derivative at point t equals to 0. So we'll just calculate this, we'll get number 2. Now we have some simple exercise here to solve. In exercise 1.3, the first step, express dv dt as a function of t. I have to express dv dt as a function of t first. Okay, and both by using the chain rule and by expressing w in terms of t and differentiating directly with respect to t. Then evaluate dv dt at the given value of t. Okay, the first one, dv dt, using chain rule. dv dt equals to, if you understand the theme good and I'm sure you want to try by yourself, so pause the video and try to calculate all of this exercise by yourself. And I'm here to calculate and to check your results. dv dt equals to dw dx times not this d, ordinary d, dx dt plus dw dy dt. Of course, okay. Derivative of w with respect to x gives me 2x times derivative of x with respect to t gives me, I think this is extra thing, we don't need that part. Derivative of x, which is cosine, derivative of cosine is negative sine, okay. Negative sine of t, then plus derivative of w with respect to y gives me 2 times y times derivative of sine with respect to t gives me cosine of t. Cosine of t equals to, instead of x I have to write that one, which is cosine t, so negative cosine t 2 times sine t plus 2 times y is sine t times cosine t. So this gives me 2 cosine t sine t, negative sine, positive sine, it's 0. And we also can calculate this one by plugging in these numbers here, cosine squared plus sine squared. So cosine squared of t gives us 2 times cosine t times negative sine t plus then 2 times sine t times cosine t. So they have different signs, so the answer is 0. And for the next one is also the same formula. I will use dv dt equals to partial derivative of x with respect to t plus partial derivative of w with respect to y times derivative of y with respect to t and others. We have to use the similar way to calculate this second exercise also, and of course for the third one the same way. In example 3 it says express partial derivative of w with respect to r and with respect to s in terms of r and s if the function is given in the form w equals to x plus 2y plus z squared and x equals to r over s, y equals to r squared plus ln s, z equals to 2r. So what to do? We'll use the formula from theorem 7, which is partial derivative of w with respect to r, derivative of w with respect to x times derivative of x with respect to r and others. So let me try to calculate this one. dw dr equals to this formula. So first of all, I will need dw dx here equals to derivative of w with respect to x gives me derivative of x with respect to x is 1, derivative of 2y with respect to x and z squared. All of them are 0, so this is dw dy. Now I need, this is gonna be number 2, dw dz is z squared, so it's 2z. I just have calculated this one, and that one. Now I need dx dr, dy dr, and of course dz dr. So the dx dr partial derivative of x with respect to r gives me 1 over s, because r is on the numerator, so the 1 over s is the coefficient, any constant number, and then dy dr equals to dy dr is this one, so with respect to r it's 2r, that one is 0, dz dr gives me number 2. So just plug in these numbers here. dw dr equals to dw dx is 1 times dx dr is 1 over s, plus dw dy is 2 times dy dr is 2r, plus dw dz is 2z times dz dr is number 2. This one is equals to 1 over s plus 4r plus 4z. So let's plug in, instead of z, 2r, because z equals to 2r, 1 over s plus 4r plus 4 times 2r is 8r, and it will be 12 at last, I think, equals to 1 over s plus 4r plus 8r equals to 1 over s plus 12r. So this is the first one, dv dr, derivative of w with respect to r. And we also need to calculate derivative of w with respect to s. So it's the same way. First we need to calculate these parts, these terms, and then these terms, or you may calculate directly here and we'll get the result this kind of. In the following exercises it says draw a branch diagram and write a chain rule formula for each derivative. First of all, I'll need to draw a branch diagram. So for the first exercise we need dz dt. So in the branch diagram's top I will have the function's name, which is z. Z equals to f of xy. This is the start of branch diagram. And x depends on t, y depends on t. Okay, that's good. So from the branch diagram I have to go to two parts. This one is dz dx and this one is dz dy. At this point I have x and at this point I have y, and they are going down. Here I have t, so here dx dt dy dt. So this is the first branch diagram for the exercise given in the first one, and then writing a chain rule gives me dz, not the partial derivative, dz dt equals to partial derivative of z with respect to x times dx dt plus partial derivative of z with respect to y times y with respect to t. This is the formula, that is the branch diagram. And you have to do this branch diagram, and this is the formula. Calculate this branch diagram and formula for the second exercise and for the third exercise also. In example 4 it says express dw dr and dw ds in terms of r and s. Okay, in terms of r and s, in order to calculate this one, we'll need again that formula, which is dw dr equals to this expression, and dw ds, which is the partial derivative of w with respect to r and the partial derivative of w with respect to s respectively. So first of all, I'll need partial derivative of w with respect to x. Here it is 2x, and partial derivative of w with respect to y is 2y. So times dx dr. It's 1, dy dr. It's also 1. So 2x times 1, 2y times 1 gives us, instead of x, I'll copy r minus s, and this was x, it was y. Calculate this and simplify, get the number 4. In the next part, which is the partial derivative of w with respect to s, I'll also need to calculate derivative of w with respect to x, which is the 2x again, derivative of w with respect to y, 2y, derivative of w with respect to s is -1, derivative of y with respect to s is 1. So calculate this expression, get the answer 4s now. And this is the next example. Use theorem 8 to find dy dx if y squared minus x squared minus sine of xy equals to 0. Solution. In the solution, we'll take the f of xy equals to y squared minus x squared minus sine xy. So theorem 8, we have to use implicit differentiation rule. Implicit differentiation, if you remember. Now we have to use implicit differentiation. We'll take f of xy as a y squared minus x squared minus sine of xy. And according to the formula given in that part, dy dx equals to negative partial derivative of given function with respect to x over partial derivative of given function with respect to y. So fx, how to calculate fx? Partial derivative of the given function with respect to x. Here we have y squared, its derivative is 0 minus 2x minus derivative of sine gives me cosine, and derivative of xy gives me y times cosine xy, and derivative of f with respect to y gives me equals to 2y minus 0 minus x, derivative of sine is again cosine xy. So I have to put this expression here and that expression here. If you look, this calculation is significantly shorter than a single variable calculation using implicit differentiation. In example 6, it asks to me finding the partial derivative of z with respect to x and partial derivative of z with respect to y, and of course calculating their value at point 0, 0, 0. The function is given in this form, so we'll again need to calculate this using implicit differentiation. Implicit differentiation. In order to calculate this with implicit differentiation, we'll need first partial derivative of given function with respect to x, with respect to y, and of course with respect to z. And we'll need to check the partial derivative of f with respect to z at point 0, 0, 0. If it's not 0, and all first partial derivatives are continuous, the implicit function theorem says f of x, y, and z equals to 0 defines z as a difference near the point. So we've calculated there the partial derivatives of x, y, and z, and just put to the formula. Dz dx formula was this, and dz, oh sorry, it was y. Here it should be y. Dy. I made a mistake here. And that will be correct, I think. Yeah, I wrote here dz dy, but there dz dx again. Now we've just calculated that and plug in 0, 0, 0. Instead of x, plug in 0. Instead of z, plug in 0. Instead of y, 0. E to the 0 times 0. So on the numerator we'll get 0, on denominator is 1. 0 over 1 gives me again 0. Or in the next part we'll get the 1 on the numerator, 1 in denominator. So negative 1 over 1 gives me negative 1, of course. Here are some exercises. Assuming that the equations in 1.3 define y as a differentiable function of x, we have to use theorem 8 to find the value dy dx at the given point. So just now we saw one example how to calculate this one. In example 6, use the same method to calculate these exercises. Good luck guys, see you.